Hello, this is Thomas Cornett presenting on behalf of Group 1 for INDE6332 project number 1. This project tasked us with determining an optimal project vessel design configuration using the constrained weighted factor project selection method. In this project, we evaluated multiple vessel configurations and applied a structured design model to recommend a single optimal design. This presentation walks through our project scope, evaluation methodology, and final recommendation. I'll briefly explain how we structured the decision model, how each design characteristic was evaluated, and how we arrived at our recommended vessel configuration. I'll begin with a high-level executive summary. We applied a constrained weighted factor decision model to evaluate 24 possible vessel configurations across size, hull material, engine configuration, and cabin design. Evaluation factors were selected to reflect safety, performance, cost, operability, and life cycle considerations relevant to the intended operational environment. Each configuration was scored using normalized factor weights, and minimum constraint thresholds were applied to ensure that unacceptable trade-offs were excluded from consideration. Based on this analysis, the 34-foot aluminum hull vessel with a single diesel engine and a half cabin achieved the highest constrained weighted score and is recommended as the most promising candidate for further development. Next, I'll outline the project scope. This analysis evaluated 24 predefined vessel configurations using fixed design options provided in the project requirements and assumed a Texas Parks and Wildlife operational context. Relative factor scoring and normalized weights were applied to ensure consistency across all configurations. Minimum performance constraints were enforced to prevent designs with critical deficiencies from ranking highly. This study was intended for concept-level selection and does not represent a final engineering design. The first design characteristic evaluated was vessel size. We considered three size options: 34 feet, 36 feet, and 38 feet. Size directly affects stability, onboard workspace, fuel consumption, and maneuverability, all of which influence operational effectiveness. While larger vessels generally provide increased capability, they also introduce higher operating and maintenance costs, which were captured through the weighted factors and constraints in the model. The next characteristic evaluated was hull material, with fiberglass and aluminum as the two options. Hull material influences durability, resistance to the environmental exposure, repairability, and life cycle cost. Aluminum offers advantages in impact resistance and field repairability, while fiberglass can offer low initial cost and smoother ride characteristics. These trade-offs were quantified using the same global factor set to ensure a consistent comparison across configurations. Engine configuration was the third characteristic evaluated, comparing single diesel and twin diesel options. Engine choice affects redundancy, fuel efficiency, maintenance complexity, and long-term reliability. While twin engines provide increased redundancy, they also introduce additional cost and maintenance burden. The constrained weighted factor model allowed us to account for these trade-offs while preventing configurations with insufficient reliability or performance from scoring favorably. The final design characteristic evaluated was cabin design, comparing a half cabin and a three-quarter cabin configuration. Cabin coverage impacts crew protection, available workspace, visibility, and overall mission flexibility. While increased cabin coverage can improve comfort and weather protection, it may also reduce open deck space and visibility. These considerations were reflected in the factor scores and applied consistently across all configurations. This slide summarizes the constrained weighted factor matrix used to evaluate all 24 vessel configurations. Each factor was assigned a normalized weight, with the total weight across all factors summing to 1. For each configuration, factor scores were multiplied by their corresponding weights, and only those contributions meeting the defined constraint thresholds were included in the final score. This approach ensured that strong performance in one area could not compensate for unacceptable performance in critical areas. Based on the constrained weighted scores across all 24 configurations, the optimal design configuration identified was a 34-foot vessel with an aluminum hull, a single diesel engine, and a half cabin. This configuration achieved the highest total constrained score, indicating the best overall balance of safety, cost, efficiency, and operational effectiveness within the defined scope and constraints. As a result, this configuration is recommended as the preferred candidate for further evaluation and potential development. This concludes our presentation. Thank you for your time, and we welcome any questions or feedback regarding our methodology, assumptions, or final recommendation.